Open up for questions. I will briefly discuss the stuff, the Friday before spring break, just to kind of refresh your memory on what they mean. Just to try to be as fair as I can. If you email to me, like, I mean, I'll take a list and shoot it. I mean, it'll be some points
I
off.
thought I heard Wednesday night.
When did you put that, buddy?
I mean, you can submit it with a penalty, but I'll accept it. You just have to email it to me because it's Blackboard blocks it.
Are grades supposed to work?
For the homework?
Yeah.
No, because it was just due 7 minutes ago.
Oh, yeah, you're right.
Like, I mean, I don't know what you think I can do, but it's not that.
Yeah, high expectations.
I mean, I appreciate it. I appreciate that you have this high expectation of me. I'm sorry to disappoint you.
You're not disappointing me at all.
Okay. So let's take a look at this data. This is the problem you're working on. For the homework, we're doing a kinetic model. And I didn't, like, it's more about putting in an honest effort on this one, because this was not a simple problem to solve. So, we have, this is our model here, this R equals KC, B raised to B0 times D raised to D1. But the thing that you have to keep in mind with that is that we have our K value, our kinetic parameter, which is also an equation in and of itself, so you have to embed these. So you end up getting R equals, I'm gonna write this out in a big ugly thing, A exponential of negative EA over RT times the concentration of C raised to the B0 times the concentration of D raised to the B1. Oops. So this is, you have to put them all in one term, which means you're regressing your A value, your EA value, your B0, your B1. You have 4 parameters you're going to regress here. So, let's go ahead and write this. Let me put, actually, a couple more spaces just to make sure I have plenty to work with. Okay, so we have A, EA, B0, and B1 as what we're trying to predict. Now, to do that, we're now going to just put in approximate values right now. And I'm just going to start with like 1, just because to give it something to jump off with. So now I need to do my Y predicted, which is R. So I'm going to just call it Y predicted, so that we'll give the kind of we use. But this is basically our new R naught or R0 value. We also need to know some constants in here. R 8.314. This is joules per mole Kelvin. This is your gas constant. Again, I recommend that one because this is we're dealing with activation energy, which means we probably want an energy term in there, so that's an R that has an energy term in it. You could have used 0.08206 atmosphere liters per mole Kelvin, done all that the same way, and been perfectly fine. Another advantage of this one is your temperature's in Kelvin already. This is a Kelvin term, so you know you're working with kind of the same situation. One thing to notice is the difference in your reaction rates, or your values. Your reaction rates in micromoles, your C and D are in millimoles. So, we need to make sure to take that into account when we update our fit for our data.
I use 0.082. Is that okay?
You use what? 0.08206?
Yeah.
I mean, as long as you do your units analysis, you can. Yeah. Like the key is recognizing what the use, because right now you're regressing parameters. These have to have units on them. So make sure that your units reflect whatever you regressed your model to. So that would mean if you did moles, atmosphere liters per moles Kelvin, that would mean it'd be moles per liter atmosphere for your activation energy, which technically are units. They're not an energy unit, so you probably want to convert it later. But if you're not asked to present specific units, it's all in particular units. It doesn't matter what you choose, bless you. The key is just make sure that you write, like, and that's something to think about whenever you regress a model, make sure you, when you give the values, give units, because they're gonna be depending on what you chose. So my y predicted is going to be A, we're gonna lock that, F40, times the exponential of, and I always just -1 times, I could just do negative, it probably would work, but I was afraid it's gonna screw it up. E over, our R is a constant, so the good news is you're not regressing anything there, that just stays. And I'm just gonna divide by R divided by T, so I'm gonna put parentheses in because I'm lazy. There we go, that's my K term, that's all this right here. Then that times CA raised to the B0, so I'm going to go ahead and put those in parentheses so that I keep the exponent where it needs to be. C raised to the B0, and again, block that, times D, parentheses, D raised to the B1, which is this one. One thing we could talk about, just as not for today, but after the exam, is have you ever done where you define your cells? You can give a name to a cell. So like this is cell B11. I could actually call it R, or I could call it like GC for my gas constant. And now I can just reference it as GC in my equation of what I'm going to do. I'm going to put it back at B11 so I don't break any of my equations. Okay. Copy this down. And now we're just going to regress it. And to do that, we need to calculate some values, right? What information do we need to do a regression? We need residual. So that's what we're going to do, is residual of y. So that's y minus y predicted. So that's my y minus y predicted. What else do I need? I need my squared, right? My squared residual. Instead of, I like to do it in a separate piece so that I don't have to carry it around and do squared and other equations. So my residual squared, I have that. Other thing I'm going to need to calculate, my mean of y. And I'm going to need that for my TSS value. So equals the average of y. So I've got that. So now I need to calculate my yi minus y bar. Or the average, y bar is y average if you are not familiar. Are you all familiar with that? If you put a line over, it's the average? Yes.
You took the mean of the first column or y predict?
Of your actual y's. The mean of the actual y values. So what the TSS is doing is it's looking at the variation in your actual data and using the variation in the residuals to try to minimize that. Because variation in your actual data is what's expected. It's basically what you expect from your process that variation to be. So what's saying is basically anything it scales it by that. It's like, this is what I expect it to be. Therefore, if it's inside this, it's going to be a smaller number. Versus it trying to use just pure residuals, that can be a little more challenging. So this is just a way to normalize your difference. So now it's yi minus y bar, which is your mean. So we're going to lock that. going to square that. So yi minus yr squared. I'm squaring that because we're going to need it for the TSS. Okay. Now, we need RSS and TSS. RSS is just the sum of your residual squared, so that's just the sum of that. Your TSS is just the sum of your yi minus yr squared, or yi minus y bar squared. So it's this. And what's the last thing I gotta do? R squared. What's the equation for R squared? Yep, 1 minus RSS over TSS, which this is at the end of one of those times where I could use variables. I could define those as RSS and TSS and just type them in. It makes it a lot easier than having to remember, oh, that's this, that's this. It makes it just, I actually like that technique. RSS, and here I'm not gonna lock them because I'm not moving it, I'm not copying this. Okay, so my R squared is garbage. I mean, it's negative 0.621 e to the minus 1, that's, I'm gonna convert this to just general, there we go, so we can see it in the way. And so now, we're just gonna regress this. We're gonna go data, solver, I know. And we're going to try to maximize our R squared. And remember, the highest it can go is 1. Based on the variables we're changing, so this is gonna be good. By changing these 4 terms, we're gonna talk about constraints later in class, where you're going to actually add constraints to your system. Like, you know, a value can't be negative, or it has to be greater than 0, and it has to be less than a certain value. You can actually put those constraints in there, and it'll move your variables within those. We're not going to make any of them non-negative. We're not going to constrain them as non-negative because we don't know, and we're just going to solve it. And we get that. Whoops. Why didn't you keep it? Let's try again.
Mine was kinda giving me errors yesterday.
There we go. You have an error?
I was getting some yesterday, but I finally got an error.
What do you get?
No, I got it now.
Oh, you got it? Oh, kill those. That's why. That's because I was playing with some restraints on the system. So if you're getting errors because you have the constraints in your system, you have to delete those.
Yeah.
There you go. And so what you end up with is your A is 0.4817, your EA is 1. Under these units, you have to do obviously calculate your units and everything. Your B0 is 3 and your B1 is 3.86. And we have an R squared of 0.998251. That's pretty good. What we're going to do is we're going to plot our R versus R predicted just to see how they look. We're going to do, actually, we're going to plot R, yeah, we'll do R versus R, R predicted. So insert.
So it's calling
That's weird. That's like, remove all these things. We're going to do our Y as our X value here just because. And I have to do one versus the other. And then our Y predicted. And this is Y versus Y predicted. And ideally, we see what we see here is a 45-degree line. That means that our predicted and our actual values match very, very well. That should, anytime you plot the predicted value versus the actual value after you regress it, that should become a 45-degree line. If it does, that's just another sign that you did, that your prediction is good. We have a couple points that are like slightly off, but really not enough to matter. And so if you want to verify this is a 45-degree line, go here, add a trend line, display your equation on your chart, and you got that the slope is 0.9972, that's pretty close to one, right? So that's, and for a y versus x, a y equals x chart, your slope is one. We're close to one. This intercept is 0.8351 on a scale from 1 to 1,000. I'd call that 0 for approximation purposes. So looking at this, our data fits extremely well, what we'd expect.
I think it just is R.
What's that? Now, that was the next question, is we need to do adjusted R squared, right? Why do we need to do adjusted R squared?
That's very multiple.
Right, we have multiple predictors, we have multiple independent variables, which means R squared really isn't the best measure. Adjusted R squared is. So we need to do adjusted R squared. And this is an equation that it always slips my brain on what it is, so we're gonna Google it real quick because it's you actually, and also at the exam, you'll have open book, you'll have your open notes, so.
It's 1 minus n minus 1 divided by 1
It's-
minus, or n minus 1
But it's
minus
P, yeah, okay,
times.
so it's one,
So we're maximizing.
I'm just gonna write the equation in here, so it's,
By changing.
stupid meeting that I told them I couldn't make. Adjusted R squared, I'm just gonna put the equation here, equals, 1 minus n minus 1, this is the numerator, n minus 1, divided by n minus 1 minus p times, it's basically 1 minus R squared.
Yeah.
There. Which, we're now going to insert a couple things up here to give us some space, because we need to put in our n and our p. Okay, what does n represent?
The number of observations.
Number of observations. So this is one observation. One set of data collected at one particular condition is an observation. This is an observation, this is part of an observation. So it's basically how many rows do you have of data? And so we just scroll down the bottom, we look, we have 61. There we go. We have 39. By the way, if you don't know, they'll give you a countdown here at the bottom if you just select it. So we have 39 observations. We have C and D and temperature. So we have 3 predictors. And then we're just gonna calculate that. So we're gonna have 1, I'm gonna put the 1 minus in last so that I don't screw it up. I'll just slide it in at the beginning, so n minus 1. And again, you could lock these, you don't have to because you're not copying this anywhere. It's just gonna be this one calculation, divided by n minus 1 minus p. Now times 1 minus R squared. And then put all these in parentheses and do 1 minus that. There. And this is still pretty good, right? I mean, it's slightly worse, but that will always happen. Your adjusted R squared for a multi-predictor system, or even for if you do it for a single predictor, your adjusted R squared will always be worse than your regular R squared. But which one do you need to use here? Regular or adjusted? Adjusted, you have to, because you have more than one predictor. If you have one predictor, you can get away with R squared. If you don't, use adjusted R squared.
I use 0.083, not 1.
What's that?
I use, yes, 0.083, not 1.
That's fine. You just, that means your units are different.
But I,
Yeah, all your values are gonna be different. Because,
the powers is not the same.
and well, that makes sense, because they are, Your powers, if you use a different gas constant, your powers of those other parameters are gonna be basically the same or pretty close, because that just uses the concentrations in those information. The key here is that it is going to adjust your units on all these slightly, which is going to adjust your parameters all a little bit from what they were. Yes, sir.
So what is the regression variable?
There's only 3 regression variables. So this is your dependent variable. These are your 3 independent. So
Oh.
these are your 3. So these are your what we refer to as predictors or dependent variables. This is your dependent variable. This is the one that's your basically your reaction rate. You're not controlling this. You're controlling these. That's why I labeled them Y, X1, X2, X3. So you'll know Y is always going to be a dependent variable, and your X is always going to be your independent. And then you're fitting 4 parameters: A, E, A, B, 0, and B1. Does this make sense to everybody? Once you kind of do these a couple times, they get to be very, like you can see, it just becomes kind of second nature to just go, oh, you don't even have to think about really what you're doing because the algorithm is the same. It's the, okay, I gotta get my Y predicted, then I have to get my residuals, I have to get my residual squared, I have to get my mean value, I have to calculate my yi minus y bar, I need to square that, get my TSS, and then I can get my R squared and my adjusted R squared. It just works through that mechanism every single time. So that's why I recommend making sure you're comfortable doing this, build a sheet that you're comfortable with looking at, using it as a template, because then when you have to do this in the future, this is what it looks like. It's the same. It's just all you adjust is, okay, what parameters am I regressing, but you're still gonna need N, P, obviously R is your gas constant, but you're gonna need mean, RSS, TSS, R squared, or just R squared. Like, you're just gonna need those. So if you build a template that has it, your life is easier. And then you just adjust the references and make it work. So how'd y'all do on this last night?
Terribly.
Terribly. On this one, I expected to be a challenge. I'm grading on this one purely on did you put in a good effort. Because I'm also now going to post this solution, so you'll have it. You'll have my solution, you'll have your solution. The key is if you use, remember, if you use different values for your gas constants and stuff, make sure to adjust if you're gas per units, adjust your units to match. That's gonna be the key. The good news is that the only thing that really affects from a computational perspective is it will adjust the value of your K. Actually, will it? It shouldn't. No, it may adjust the value of your A, but not necessarily because but the exponential term is all unitless, right? So it'll adjust the value of your activation energy to adjust for the different parameters, but that's still going to be unitless. So you know EA has to match to make that unitless, and then your A will have to adjust because your EA is going to be different units, but your A is going to have set values, right? Because if we look at your exponential, so this is where the slightly difference in exponential will change it a little bit on your units. These are in molar for your C, so but your exponents should be unitless. But your A has to give you output of micromoles. So make sure that you adjust your K, your A, for K to have the right units. It doesn't matter what units you use to regress as long as you document your appropriate units to make sure things match up. That's all. And make sure it's a valid value, obviously. Don't use a gas constant that doesn't exist. Because there's like 1.987 is another gas constant I think you can use. I don't remember all the units on those. I had a table of like 20 at one point, but I just remember 08206, 8.314, those are the big ones. And I think there's one that's like 1.9 something, right?
So we can definitely expect to have to do this on the exam, probably.
No, absolutely. I mean, 1.986, there it is, BQs per pound mole degree ranking. I knew there was one that was like that. Yeah, so the ones I know are this one, well, that's the same as atmospheres liters per mole cup. Yeah, 8.10806, that's the one I use. Versus, yeah, bars per these are large pool common. Yeah, so this is just one of those, depends on what units you're used to using. Okay, so because it was brought up, I'm going to go ahead and discuss the stuff for, the spreadsheet that I went over in class the Friday before spring break, so let me. We're not gonna go over it in great detail, but I am gonna go over it from the perspective of. On basically what are the general concepts in it, so that you can feel at least a little more comfortable in it. So let me pull that up. Like I said, you are, while I'm pulling this up, format of the exam, everything is through Blackboard on this one, so that's all collected in one space. You're going to have your multiple choice, true, false, matching in Blackboard. So you're just gonna answer it in there like a standard exam in there. When you get to the last problem, it's gonna be a calculation problem. The Excel spreadsheet is in there, you can download it, work it, then reattach it before you submit your exam. I encourage you to go ahead and download it, do the regression, and upload it, because at 10:10, it will force submission of your exam. So get the math problem done first, the regression problem done first, and then go back and do the multiple choice. Don't get trapped in doing the multiple choice, because I think it's, the way it's set up, it's 68% of the grade is multiple choice, fill in the blank, so forth, 32% is that problem. It's not, that problem is not gonna take that long, because it's basically what we did here. So if you're comfortable with it, you have those toolkits you've already built. You can obviously use those templates to help you. It will make your life easier if you just do that first, get it uploaded so you have to think about it. Because if nothing, think of it this way, if you're working the multiple choice and you get 90% of the way through and it submits, but you've uploaded the problem, that would mean you can get basically, out of 68 points, you could get, 62 points. And if you get a 30 out of 30, that's a 91. If you're doing the problem in Excel and you haven't attached it, but you're 90% done, it doesn't care. It doesn't see a file there. It gets shipped up. You get a 0 out of 32, even though you did 90% of the work. Do that first, because that one is a all or nothing, like from a submission perspective. The multiple choice, if you just don't get through all of them by the end, not a big deal. You just lose what you didn't get through. That one, it's, you don't have a file attached, you're kind of stuck.
So you said it's just one problem?
Just one problem. Yeah. I can tell you, and I don't know if this will give you any peace, I worked through the whole exam yesterday, it took me 22 minutes. So, like I said, if you're really comfortable with it and you know how to do the stuff, you know exactly what I'm looking for, you can knock it out in 30 minutes. If you need more time to think about it, you still have another 30 plus minutes to kind of think and decide stuff. So, ideally, it puts you in a good position to figure it out. If you have a good jumping off point, how to figure it out. If you're completely confused, you're kind of stuck there. But I think that kind of goes without saying anyway. Yes, ma'am?
Are you gonna be strict on us having the same final answers as you?
No.
Because I feel like depending on the guesses you put in Solver, it'll find you a solution.
Yeah, no. Now, I will tell you, I designed this one, it should regress to the same value regardless of what you put in your starting parameters. I made sure, so this is something we're gonna talk about after this exam, is robustness of your model. Sometimes we saw that with an oscillating model. Depending on where you guess, you can get it to solve two different solutions. This is where designing a good, robust model that doesn't have that problem comes in, and that's where sometimes you have to adjust like your units. Maybe one of your parameters has units from 0.00001, or has values from 0.001 to 0.003. And so what happens is it doesn't appear, if you build your model wrong, that doesn't adjust it much. So you sometimes have to scale or normalize all your data to where they're the same scale, so they have enough of an impact that doesn't happen. We'll talk about what that looks like, but I did make this one where it should converge to the same value regardless of what you guessed. I think I guessed things starting at 1 up to like 10,000 and it still got there. So, now, that being said, don't start with 0, because sometimes it just doesn't like 0. So never start Always put a seed guess in that's not zero. Because otherwise it falls on its face. Okay. This is right. Yeah, okay, cool. Let me unfreeze this. I already did. Cool. Okay, so let's talk about this real quick. I'm looking at this. We talked about ways, so we talked about identifying outliers. What are ways that you can identify outliers when it comes to a single data set? Not Y versus X, you just have a data set of Y values. How do I find my outliers there? Do y'all remember this? It was before this one, it was the lecture before this one. It doesn't fit, but how do we measure? How do we determine, we validate that a data point doesn't fit? So let's say I'm looking at grades of everybody in the class, and I want to know if one of them is an outlier. How do I identify if that's an
Yeah,
outlier?
like the Z-score.
Yep. Z and modified Z. Those are your two ways to do it. Right? Z-score is value minus the mean over the standard deviation. So it's basically saying how far from the mean value are you? So that's basically all you do for every data point. You do yi minus, or if it's x, xi minus the mean of x over standard deviation. What is the threshold for z score to be an outlier? Y'all remember? What's that?
One?
Yep, there it is. 3. You hit 3 standard deviations, that's above 99% chance of it. Basically, it says that there's less than a 1% chance that you're a real data point. Because if you look at the standard deviations, it's like 68, 95, and 99 point something for 3 standard deviations. So above, if you're outside, if you're plus or minus 1, so it's 3 or minus 3, those are your ends. If it's above 3 or below minus 3, it's an outlier according to Z-score. Because it says there is a less than a 1% chance that you are a real data point. And so it's perfectly valid to say, yeah, we're going to ignore that. Now, what's the biggest assumption from Z-score? And why we went to modified Z-score? Y'all remember? What's that? It's not necessarily linear, but it has to do with the shape of the data. Normal. Z-squared assumes you're dealing with a normal data set, meaning it's normally distributed bell curve, that classic shape that you always see. The problem is, do you know if your data is normally distributed?
No.
Generally, no, not unless you're told, or you've sampled it and you threw it on a bell curve and it looks normally distributed. You really don't know. So what do we use instead of Z-score for that purpose? We use the modified Z-score. Modified Z-score doesn't care whether it's skewed data, doesn't care whether it's like there's a large span of the data or anything. It actually fixes that. Because it doesn't use mean anymore, it uses median. It says, hey, what's the middle of my data? And it adjusts based on median, not mean. And so it does yi minus y median over the median average deviation, or the median of the deviation of the system. And so just remember that equation. It's in your notes. Hopefully you still have it in there. If not, you can definitely Google it really quick. Like, it's not a big deal. It's a little more challenging to work with, but it does give you a much better representation of outliers than standard Z-score does. Modified Z-score doesn't care about the distribution of the data. It just does it. What's the cutoff for modified Z-score?
3.5?
3.5. So it's slightly higher to get an outlier in modified Z-score, but it doesn't care about the distribution of your data. So it's a far better measure of doing that. Okay, that's if you have a single piece of data, right? That's like a set of Y's, a set of X's, whatever it is. What if I have a Y versus X, or Y versus something? What do I do? This stuff. This is where you have a graph, and you're like, okay, I'm going to look at my data and make a decision. And so if I have Y versus X, I'm going to look for types of outliers. I had 2 types of outliers. What were they? Yeah, it's an X outlier and a Y outlier. How do I define an X outlier? yeah, it's basically far off on the right. So what I do is I draw, imagine I take a bunch of my data and I have one point that's like out there that I think might be an outlier. I draw a box in my X and Y to capture all the other data points, just barely. If that point lies within the Y range, but is far outside the box from the X, that's an X outlier. It's like, this is a Y value that's in the range I would expect, but the X value looks weird. That's considered an X outlier. By the same argument, that's the opposite that's the inverse of what a Y outlier is. A Y outlier says if I look at all the other data and I put it in a box, it's in the X range I expect, but it's too high. It's outside that box. The reason we have to define it by only one direction is because we have the other types of points that we've talked about. And the big one is the leverage point. A leverage point is like this guy out here. You might think of it as an X and a Y outlier. But the problem is it's not really an outlier, because if you look at the regression, it actually still fits it pretty well. That's why you can't call it an outlier. We never refer to it as an outlier, we refer to it as a leverage point. The reason we refer to it as a leverage point is because it influences this model far stronger than any other data point does, because of how far out it is. Think of it as like basically these become a pivot point around moving that one. And because of how far out it is, if I move this line, so look at the blue line versus the orange line. Do my residuals change much for these parameters down here? No. But if I consider the blue line out to here, what about a residual for this one if it were the blue line around here? A massive difference. That one residual swamps the other residuals and causes the model to try to fit that point. And that's why it's called a leverage point, because it forces the hand of the model to fit it, because it is so far removed from the other data. Any data point that's way out, but seems to still fit the data well, can be a leverage point, and you truly try to remove those if you can. If you can't remove a leverage point, your next option is to fill in the data around it. Close that gap. Eliminate residual points by making sure that the spreading your data is not huge. Big gaps in your data, I should say. Like, you can have it be from 0 to 25, no problem, but make sure that you have this whole range covered. Don't go to 10, then all of a sudden we're at 20. That one point is going to cause a massive problem. It's too influential. It's a leverage point on your system. Which brings us to the other concept of an influential point. An influential point is not an X or Y outlier. It is within the box. Like this guy right here, like this one data point over here. It is within the Y box, it's within the X box, everything fits. But that one data point can cause a massive shift by adding it or removing it. That point is unduly influential on your data. How do I decide if it's an influential point? Visualization. Does it make sense when I look at it? If all these other ones fit this straight really well, but I have this guy down here, I have to question whether I can keep it or not. Now, what you can do is add it, remove it, see how your model behaves. If your model still fits well with the other data by removing that one, and it actually maybe even helps your model a little bit. Like here we go from a 0.479 or 0.699, 0.9746 by dropping that one data point. You can see how much it's influenced our model by just being there. But it's not a true outlier because it's within both ranges. If you have an influential point, you do this, you show the difference, and you go, it's actually better to remove that point for this reason. The X outlier and Y outliers are straightforward. If they're an outlier, they're outside your range, you can just go, yeah, we'll feel that way about it. But you can't do that with a pure influential point. And of course, a leverage point, throw it away or try to fill in the data if it's available. Is this comfortable with all this? The other thing we talked about was doing your residuals. So with that one, just like we did before, if you want to look at whether it's if you have a mixture of data and you have to figure out your residual behaviors, you can also do residual analysis like this, where you can have multiple X's and a single Y and figure out the residuals, and then do the standardized residual, which for a standardized residual takes your residual and divides it by the standard deviation of your residuals, to just say, okay, basically it converts it into a normalized thing that we're used to seeing. And then you look for that, is it 3 outside? If it's a residual that's more than 3 standard deviations from the mean, cool. Then we can neglect it, we can get rid of it, and we don't have to deal with it. You can also do deleted. I will tell you now, you're not gonna be doing this on the exam because this takes a while to do, as you learn from doing this. I just wanna remind you of this. You can do like deleted predicted Y, which is where you say, okay, I wanna know if this is a residual, so I'm gonna take this data point out. I'm gonna do my residuals, do my regression residuals for it. I'm gonna then say, okay, what would it predict for that value if I put it in, if it wasn't there? Then I do the predicted versus what it actually read, and I do that for every single data point. And then I can do that and look for the standard deleted residual and whether it's above 3. You are not gonna be doing this on the exam. This takes too long to do by hand, so I'm not gonna ask you to do that. Yes, sir.
For the exam, will it be more of what we did, like, in the previous exam also?
It's gonna be a mixture of this and what you did this last time.
Okay.
Yeah. It's gonna be less of the calculations of this, and it's gonna have like the theory from this we just talked about, like types of outliers, how do you know what they mean, like the concept of z-squared and z-score and adjusted z-score, or modified z-score, and then get the other stuff, we're gonna look at R-squared, adjusted R-squared, and regression analysis around that. Any questions? Is there anything that like you're just not comfortable with so far? Or is it one of those things that like, it makes sense, you just kind of need to look at it some more? Okay. I think, like based on what I saw in the scores in the first exam, I imagine the average will probably go up. I mean, the average wasn't bad on the first exam, but this was also the first time you're seeing this type of material, the first time you're taking a test with me on this type of material. Now that you know what to expect, it's gonna look a lot like what you had in the first one. A lot like it. The only difference is instead of by hand filling out a paper, you're gonna just do it in Blackboard now. It's just easier from a bookkeeping perspective. Instead of me handing back papers, you're gonna get feedback on there, so it'll be immediate. Not immediately, because I'm not gonna let it post immediately, but you'll know quickly what your grades are. It'll just save some time. I think, hopefully this is starting to become a little more second nature to you. I know it's just practice, but hopefully you're getting comfortable. Did the homework last night feel more comfortable than what you had been doing? Is it one of those things where you're starting to feel more comfortable with the concepts? Yes, no, like, I see anxiety, so.
No, I made a mistake. I thought it was doing Friday.
If you didn't submit, you thought it was, oh, it's coming Friday?
Yeah.
Yeah, if you want to submit it late, you can email it to me, you'll just take a penalty for it being late,
Okay.
but you can still submit it. Because I'm grading this one on effort, so it's really about did you put in the effort. Because I understood, like, first time you're trying to do this, but I want you guys to at least try it, and then like, that's why I went over it last day, so that you could then adjust, fix your spreadsheet, and know exactly what you did differently. The key is, we haven't, like I said, the one thing that we haven't talked about is that units matter, and they do, and we're gonna talk about how you can adjust your units to help benefit your regression analysis. You're gonna find that if you have one parameter that's just a overall are larger values than another, like if X1 is just 2 or 3 orders of magnitude bigger than the other X's, it can cause your model to be overly influenced by it if you don't normalize your data and then look at it. And then you denormalize the model when you're done. So we'll talk about how you do that too. But it's not anything major. That's kind of like, now we're gonna be getting into the steps that are specific to solving what our topology is gonna do. So on Monday, we'll go over the exam, and then on Wednesday, we're actually gonna start, I'll be giving you data sets to start, like, basically giving you sources of where data sets are, and you're gonna come together as your groups and start picking, like, okay, I wanna do a regression of this, and we're gonna look at stuff like from DOE, from NIST, from NIH, like actual data sets they have available from research to look at whether you can regress behaviors out of them and find something useful in other people's research, basically. So real data. So we'll see. I have not looked at a lot of them. I have no idea what you're gonna find. I want it to be completely open-ended. I want you guys to pick the parameters you think are interesting and see like what the behaviors are. So I want to leave the projects as open as I can. That means that I don't know, there's not necessarily a right or wrong answer. It's really about, are your methodologies good? So when you're doing the project, just like with the exams and with everything else we're doing, show me your methodologies. That's the biggest thing. If your techniques are right, your methodologies are right, the results are what they are. Like, that's the reality of any of this stuff, is your regression is whatever it's gonna be. But did you get there the right way? And if you did, cool, no problems. Okay. Get here before 9:10 on Wednesday. That way you have time to get logged in. Denise will be proctoring because I'm going to be showing our speaker around campus and taking them to breakfast. So we have that. And you all are welcome to come to the talk at SciTech 103 at 1 p.m. on Friday. He's the department chair of Villanova. He's going to talk on sustainable materials for concrete using magnesium, like chloroxides, I think, is the structures of them. They're environmentally friendly. He's a nanoparticles, nanomaterials expert. Also just a really nice guy. I've known him for forever now, 22 years, so known him for a while. So I encourage you, if you've done anything going on that window, listen to him talk. He's really good. He's a really nice guy. Those of you who were at AICHE this last year, and if you helped out with him, you may have seen him stop by. So, like I said, I've known him for a long time. Any questions? Any concerns? Do you feel more comfortable about this exam than you did the first one?
Yeah.
Good, that's good. I expect that the scores will be better. Like I said, the scores weren't bad on the first exam at all. It's just more I know getting comfortable with, this is brand new material. This is new concepts you've been exposed to. Like, this is not trivial to grasp, but once you get the hang of the algorithms, they're repetitive. You then know exactly what you're looking for. And what ends up happening is you can actually analyze data knowing nothing about it. Like, somebody just gives you a data set and you could regress it, you'd be like, well, what's it mean? I have no clue. But this is how the variables react to each other. And this is what like basic data mining experts do all day long. It's just, they're given a data set and like, figure out if there's anything useful in here. And you just do these massive regressions and then look for behaviors. So you look for covariances and correlations and try to analyze that and say, okay, what's useful? So what we're going to talk about after this exam is, you're going to start with like 1 Y and for your project, maybe 20 X's. But the question is, how do they influence it? And and your model can get very big and very ugly. So then we're going to talk about how do I identify what we call principal, principal or primary. Basically, what variables are the primary influencers? And you're going to find out that you can do an analysis and say, well, these 3 account for 99.2% of the variation of this variable, so I'm going to ignore the other 17. Or maybe you'll pick up the 4th one because that gets you to 99.3%. And you're like, good, that's good, ignore these other ones. So you're going to learn like how to identify what variables are important and what aren't. We already talked about how the coefficient tells you, but this is actually just an entire technique that will tell you this data and identify it. And you're going to use 2 words that you've probably heard and hate, and couldn't tell me what they are. Eigenvector and eigenvalues. You've heard them, right? Do you remember anything about them? I never do. In all honesty, I learned eigenvectors and eigenvalues, had no idea what they were useful for until I started getting this. Eigenvectors tell you the direction of change in your data. And when you're doing regression analysis, that's important because, like, hey, most of your change occurs in this direction. Well, that's this variable. Cool. That tells me use this variable. And the second most popular direction of change is this one, and that's this variable. So this is how it identifies what pieces. So you're actually going to see how eigenvectors and eigenvalues are actually useful and meaningful versus these anomalous linear algebra things that just exist. Okay? If there's no questions, be here at 9. Actually, I might be back by 9:10. Yes, sir.
I have a question. after
Sure.
that.
Oh, you can ask now if you want to ask it. Okay, yeah, I'll take a look at it after that. Yes, ma'am. For front, the front of the first break? No, that was those were the notes. Yeah, and then I talked to the board, but.